Alright, so we're looking at section 1.7 on linear independence. So we're thinking, okay, what's the solution here? What is the solution for this, like what's going on? That we have, and we thought about this before, where we had, like 1, 2, 3, 4, 5, 6, and this weighted vector 2, 1, 0. And we're multiplying this by x1, x2, x3, and that gives us a 0 vector. What's the solution? Do we have a solution? What's our solution set? And is our trivial solution the only solution? So these are kind of like the big questions that we have. The existence of a solution. And if that solution exists, then it's the only solution. Because we know the trivial solution is going to work, but is there any other way? And so, let's look at this definition. We have an index set of vectors that are V subscripts things, and they're in Rn space. And these vectors are linearly independent if our vector equation, where we are weighting these vectors with weights x1 through xp, if that has only the trivial solution. So we have linearly independent vectors if the only solution that gets us to a 0 vector is the trivial solution. Our index set of vectors is linearly dependent if we have weights that are not all 0, but that we still get our 0 vector out. So linearly independent means that the only way to have a 0 vector come out is the trivial solution, where all of our x1 to xp, these are all 0. If that's the only way to get out our 0 vector, and linearly dependent if that's not the case, if there exists weights that are not all 0, such that we get out the 0 vector. So, let's look at this example. This is our example from the beginning. Is this set of vectors linearly independent? So, we're figuring out if it's linearly independent, and if it is, then we can find a linear dependence relation among them. So this is what we're going to put into MATLAB, and we'll see how this goes. So we have MATLAB, and so let's hit enter on this and see what we get. And this is our answer. So this is our reduced row echelon form with our augmented matrix with a column of zeros, and we have this as our MATLAB output. Okay, so what does this mean? This means that when we have x1 that equals -2 x3s, x2 is negative, oh, that's not a negative, that's a positive 2. -1 x3s, and x3 is 3. So what does that mean? That we have our solution be 2, -1, 1, for some k in our reals. And what does that mean? Well, that means that we have a solution that's not just the trivial solution. And so, since we have a solution that's not just a trivial solution, then our set of vectors is linearly dependent. So, how can we find a linear dependence relation among these? Well, Well, let's just choose any k. Do you want to choose like 7? Sure, let's choose 7. So if k is 7, then our linear dependence relation is going to be, let me sneak this over, 7 times 2, negative 1, 1, and that gives us a linear dependence relation of 14, negative 7, and 7. So if we're weighting v1, v2, and v3 with these weights, then we have a linear dependence relation. I forgot a vocab. This is called a linear dependence relation. Right here, linear dependence relation. And here's another thing that we should probably address, that the columns of a matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution, meaning that only x, the vector x equals the vector 0 is the only solution for AX equals 0, that equation. So for this example, how are we going to determine if the columns of the matrix A are linearly independent? Well, let's think about AX equals 0. If that only has the trivial solution, then our columns of A are linearly independent. So let's think. We need to row reduce an augmented matrix, so 0, 1, 5, 1, 2, 8, 4, negative 1, 0, and then a column of zeros. If you want to do this in MATLAB, you totally can. To get a column of zeros, you just tack on zeros, like 3 rows, 1 column, and that'll get you a vector of zeros. And then you can put that on at the end of coefficient matrix A. That's an option. Or you just do it by hand. And so we got tildes, because that's responsible. We get, let's swap row 2 and row 1, so 1, 2, negative 1, 0, and 0, 1, 4, 0, and then let's multiply by negative 5, our new row 1 by negative 5, so we get, and then add it to row 3, so we get 0, negative 10, plus 8 is negative 2, 0, plus negative 5 is, positive 5 is 5, and then zeros are zeros, okay? And then we can take row 2, and add it to 2 row 2's, add to row 3, so we get row 1 doesn't change, row 2 is 1, 0, 1, 4, 0, multiplied by 2 and add, and we get 0, 0, 8 times 8 plus 5 is 13, 0. And so now we have no free variables, right? Because we have echelon form. I guess we can like divide this row by 1, by 13 to get a 1 there, sure. And then we can go up and solve everything. So this seems like since there's no free variables, we only have the trivial solution. Only the trivial solution where x equals 0 is going to give us a solution to AX equals 0. And so our columns of A are indeed linearly independent. Yes. They are linearly independent. And that leads us to this, that a set of two vectors, v1 and v2, is linearly dependent if at least one of the vectors is a multiple of the other. So, if we have like vector 1, 2, that's going to equal 2 times the vector 0.51. So one vector is the multiple of the other. So these two are linearly dependent. because they're in the same line as one another. And the set is linearly independent if neither of the vectors is a multiple of the other, so if they're going in different directions. So, looking at these two sets of vectors, we have one that is linearly dependent, right? Because we have 3, 1, and then if you just scale that up by 2, then you'll get vector 2. So those two are in the same direction. And then 3, 2, and 6, 2, those are going in different directions. So these are linearly independent. So we can get them going in different directions, and so they are linearly independent. So we have characterization of linearly dependent sets. We have an index set of vectors. They're linearly dependent if at least one of our vectors is a linear combination of the others, which would result in ending up with free variables. So, in fact, if S is linearly dependent and V1 is non-zero, then there's going to be some vector that is a linear combination of the preceding vectors, like all the other vectors that came before it. So if we have two vectors in R3, u and v, the set spanned by uv is a plane, right? It's going to be this plane down here. Spanned by uv is that plane. So a vector w, so some other vector in R3, is in our span of u, v, so this plane, this flat part, if and only if u, v, w is linearly dependent. If you can get w from a linear combination of u and v. The only way for w to be in this like flat space is if we can get to w by some linear combination of weighted vectors u and v. So if in this picture, right, you have w just popping up, it's kind of off the plane, then that means that there is no way we can have a linear combination of u and v that gets us to where w is. We can get to like where this is kind of shadowed or like projected onto, but you can't get to the actual w without having like some other component, like some weighted vector from 0, 0, 1, right, to get you in this x3 direction that's off the 0. So vector w is only in span uv if u and v and w are linearly dependent. So if we have a set that contains more vectors than there are entries in each vector, so if you have vectors in our n space, but you have p vectors and there's p is greater than n, then we're going to have a set, then any of those sets is going to be linearly dependent, because we almost have like too much information that we're going to be able to, we're going to be able to make a linear combination of like our preceding vectors before we don't need all of these p's in order to get a span that gets all of what we need. So if we have a wider vector, a wider matrix than we have tall, then we're going to have a linearly dependent set of vectors, because we're going to end up with free variables. So with that, we have a set of 3 vectors that are in R2. And these are linearly dependent because we can get, if we take a matrix and we throw these into a matrix where our vectors are our columns, we have a wider than tall matrix, and we can get a linear combination of, like, we can get one of the columns from a linear combination of two of the other columns. And so, even though they're not multiples of one another, we can still get there, maybe by using different amounts, different weights than integers, but we can still get there, because these are all in, and then the span of these is R2. And so if we have a set of vectors that contains the 0 vector, then that set's going to be linearly dependent. And why is that? Well, I mean, if you just have, like, if you say v1 is going to be your 0 vector, then you can just say, okay, well, like 1, and then other zeros, as many zeros as we need, times v1, v2, and so on until p. This will still give us the 0 vector, which is a non-trivial solution. So if we contain the 0 vector, then our set is going to be linearly dependent, because we have a non-trivial solution to ax equals 0. So, which of these is linearly independent, which is linearly dependent? Well, if we have a vector of zeros, then, that's going to be linearly dependent. So LD. Let's see. What about here? Well, we have R3 space, but we're looking at 1, 2, 3, 4. Oh, that's going to be 1, 2, 3, 4. So we have more vectors than we have space, so this is going to be linearly dependent. And here we have more, so we're in R4, but we only have 2 vectors. So we can't, like, rule this out as being linearly dependent by theorem 8. But is there going to be, like, a scalar? Like, are they in line with each other? Will we multiply by, like, -2? Would that get us there? Nope. So it looks like C is linearly independent. So what did we learn? There's linearly independent and linearly dependent sets of vectors, and that we can figure out just by determining, is our trivial solution the only solution? If it is, then that's going to be linearly independent, and if not, then it will be linearly dependent, and there's some ways we can think about that, just in terms of doing row reduction. We can look at if we have free variables. We can look at geometrically, just are they going to be in line with one another? We can think about it like multiples of one another. We can think about, like, is it going to be in the span? Because the span is going to show us, like, is there enough information that we have in order to get all of the space? We can think about just comparing how much information we have in what our n space we're looking at versus how many vectors we're given. Because if we have too many vectors, then we're going to get linearly dependent set of vectors. And we can just think about, oh, well, you have the 0 vector, then you're going to get linearly dependent, because it's really easy to find a non-trivial solution if you can just use that 0 vector. All right. That's it.